Okay.
Golf Tango Papa radar heading
600 to be DM'd. 600 please at 2
How do you want Golf Tango Papa?
Down at 27.
Today's air traffic control may look chaotic, but it isn't.
Shamrock 716.
Different facilities are there to perform different tasks. Controllers in the tower are limited to the immediate vicinity of the runway. It's from here that pilots are granted their all-important slots in the sky. But another job is done in centres which are often miles from the nearest airport. Here in West Drayton, outside Heathrow, controllers are talking to pilots once they're established on their airways. In this room, as many as 40 controllers are working round the clock, handling aircraft all over England and Wales. The workload varies, but up to a dozen different aircraft carrying maybe 1,000 people can expect to be in the hands of one controller at any time. They're in the midst of a modernisation programme which will simplify their lives immensely. But even so, the task looks daunting.
At the moment, the London Air Traffic Control Centre is moving 1.3 million aircraft per year, and it is anticipated that this number of aircraft will increase progressively over the next few years, probably in the order of 2 to 3% per year. When that happens, safety will not in any way, shape or form be prejudiced. Every system we bring in, every function that we bring in is always tested very comprehensively to ensure that its safety aspects are available to us 100%.
In fact, so little do we hear of incidents that the travelling public takes the work of air traffic control almost for granted.
I've never had any upset, shall we say, where I felt that there's a risk, so I do think it's probably a very stressed job. I do worry perhaps that there might be times when people snap or just under so much stress that things are at risk, but I've never experienced that.
I feel quite safe when I'm sitting in the airplane and I hear the captain speaking and I know they have the connection with the tower. So I feel okay, I feel safe.
Do you feel safe in their hands?
Absolutely. I never had any problems with that. Not yet.
But how does it all work? The key concept is separation. In mid-flight over Northern Europe, the standard minimum under radar control is 1,000 feet vertically and 5 miles horizontally. Distances which may sound overcautious until you see this. This is what the world would look like if a car could travel at the cruising speed of an ordinary passenger aircraft. The road is slipping under the wheels at 500 miles an hour. The closing speed of the oncoming vehicles is well above the speed of sound. If anything goes wrong, reaction time is vital. That needs a great deal of empty sky. At an en route centre away from the tower, a controller doesn't see aircraft at all, but a galaxy of green blips. Attached to each one is a call sign and a code for the altitude of the plane derived from a radar interrogation of its transponder.
I'm sat in the en route operations room of the London Air Traffic Control Centre at West Drayton. In front of me is a typical radar display that an air traffic controller operating within this control room would use. As you can see, it's a 21-inch tube, and on it will be a complete picture of all the aircraft within the southeast of England. Here is the outline of the southeast of England with the River Thames and Dover's down here and then the south coast there. The controller who would use this picture would in fact have a much less complicated picture and would operate on a simplified version like this.
Whether departing, arriving or flying over England and Wales, a plane's flight details are signalled to the centre at West Drayton. The information appears on strips of paper which are given to the controllers by hand. That may seem antiquated, but information on paper won't disappear if there's a massive power failure in the computer system.
Here we have a typical strip format. On it you will see the call sign of the aircraft, and Speedbird is the call sign that British Airways use. As you can see, this is Speedbird 951 at flight level 390. He's just started his descent, and there he is there on the radar screen. The controller will route him along this route here, inbound to the holding stack. he will descend this aircraft to flight level 130, and then he will hand it over to the terminal area controller, the TMA controller, who will descend it further on into the inbound stack to flight level 70. When the aircraft has reached flight level 70, it will then be handed on to the Heathrow approach controller, who will then track this aircraft around there onto the instrument landing system to land at Heathrow.
In the early 1920s, things were rather simpler. Clearance to take off was signalled by a flag, and such traffic control as there was involved no more than a radio conversation between the pilot and the ground. Telling a pilot where he was a matter of simple trigonometry. Radio controllers in two different centres would each establish their own compass bearing of the aircraft. The point of intersection, using two pieces of string, gave the pilot his position.
Hello, Croydon. Hello, Croydon. Serial X Denmark calling.
Even by the mid-30s, the principles remained the same.
Croydon answering. Switch on your transmitter for half a minute. Over. Hello, Lim. Hello, Fulham. Your bearings, please. Croydon, 119 degrees. Lim, 168.
The only difference here was an extra piece of string to check up on the other two.
5 miles east of Dungeness.
Right up until the outbreak of war, communication between air and ground hardly changed. It was only the advent of radar which offered instant surveillance of traffic in the air. Today, the space in the sky has to be carefully rationed. Aircraft are slotted in both space and time, confined to a series of corridors through the skies, sometimes travelling half as far again as a straight line to reach their destination. This British Airways Boeing is bound for Madrid. Its journey will take it along a series of waypoints defined by ground-based radio beacons. The beacons guide the aircraft from one point along the airway to the next.
To begin with, we followed what is known as a standard instrument departure, which we call a SID, S-I-D. And in our case, we took off from the east-facing runway at Gatwick, and then when we got to a fixed distance, in this case 3.5 nautical miles from a ground-based beacon, we turned left to put us on the westerly track as divined by another radio beacon, which happens to be at Detling. But shortly after we established on that, the air traffic controller told us to fly on a fixed heading in order to ensure separation from other aircraft in the vicinity, either landing or departing from other London airports.
The pre-planned route would have taken the Boeing over Southampton, then south to Ortac on the Cherbourg Peninsula. From Ortac, the route would have gone to Dinard and then Nantes. But today, with no military traffic in the area, a controller at Brest has cleared the aircraft to fly directly from Ortac to Bilbao.
Now we're talking to the controller at Brest, making our way to Ortac, and shortly after passing Ortac we shall go direct to Bilbao, and we put that instruction into the autopilot, into LNAV, which is short for lateral, side-to-side navigation. And already the aircraft is turning, and it's going to turn onto a track which is pre-computed of 192, which is very slightly west of south.
At Belén, just north of Bilbao, Madrid Air Traffic Control takes over from Brest.
Brest, bonjour, speedbird 466 Mike.
Speedbird 466 Mike.
In which the bridging Belen, we've lost contact with your colleague on 13487. Can you give us a frequency for Madrid?
Contact Madrid on the 132.22.
13222, speedbird 46 Mike, thanks. Madrid, Buenos Dias, speedbird 466 Mike, 370 at Belen.
Speedbird 466 Mike, good evening, radar contact, proceed Somo Sierra 1 Delta.
Roger, Somo Sierra 1 Delta, speedbird 466 Mike.
Gabriel 117, contact Brest 1290, good day. 1290, Gabriel 117, good day.
Captain Orlebar's Boeing is just one of many aircraft being dealt with by a controller at any one time. Travelling across Europe, an aircraft can be passed through several different controllers. In an ideal world, traffic control would be a matter of simple coordination, well able to cope with increasing demand almost indefinitely. But in Europe, life is not so straightforward. In a world where history, politics, and national pride speak louder than common sense, air traffic control looks a complicated mess.
We have a situation in which there are some 31 different kinds of ATC systems. We have of the order of 22 different operating systems for computers, some 18 different programming languages. All of these developed independently for the provision of air traffic control, and therefore it makes it extremely difficult to convey information automatically, computer to computer.
The result is a patchwork of different separation standards, depending on where you happen to be flying. In much of northern Europe, the quality of radar coverage allows aircraft a 5 nautical mile minimum separation. But elsewhere, it has to be 10, 15, 30, or even 60 nautical miles. Aircraft can't queue up at borders like cars at a road junction. The best they can do is to fly huge racetrack patterns in the sky when they approach an area with capacity shortage. Sitting on the ground is clearly the lesser of two evils. So a problem in Greece with its 60-mile separations can create long queues for aircraft wanting to take off for destinations in the same area. But even this is not the end of the story.
Historically, the airspace in Europe is military. Only a very limited amount of the airspace is allocated to civil air transport. And there are small passages through that military area which we are allowed to use for civil. By the way, this is in strong contrast to the United States, where the airspace is primarily civilian, and if the military needs a playground or needs some area to train or whatever, it's assigned to them. But in Europe it's the other way round, and maybe it had good historical reasons. After all, the two blocks, East and West, had their border line or the confrontation line here, or in Germany rather. But I mean, we claim now, I think, with more right than before, vis-à-vis the military. I mean, the enemy has disappeared.
More than 30 years ago, in 1960, Eurocontrol was set up here in Brussels to establish uniform standards throughout the continent. But since its infancy, Eurocontrol has been dogged by that familiar equation, that ministers who can take decisions aren't experts, and that experts don't have the power to take decisions. The option of getting rid of all the different systems and replacing them with one has been rejected. Instead, Europe's in the midst of a complex 10-year harmonization program based on the existing different systems. It's a process that's proving painfully slow.
No one is in charge of air traffic control in Europe. That is exactly the problem. A committee is in charge. You cannot run a company with a committee. No one is in charge. Everyone would probably agree that we need one standard, as long as it's my standard. That is, in fact, what we see in many fields, and which is now also repeated in air traffic control. And everyone says, yes, one standard, but my standard.
While the politicians agonize, a jumbo jet burns a litre of kerosene for every wasted second that it's sitting on the ground. Over $5 billion a year are lost while aircraft wait in queues. Delays are just one symptom of the lack of compatibility in Europe. Despite improvements this summer, the Civil Aviation Authority is still nervous that a drop in investment in Britain will bring back the painful congestion of the 1980s. Once you're in the air, the wastage continues. Flying across Europe has been compared to driving across London while sticking all the time to the side streets.
You fly in airways, and these are like congested streets, and someone must decide from the ground who is let in and at what distance he can sort of approach the crossing of that street. So we are far away from what we may have one day, which is called area navigation, meaning that you would leave the narrow airways and that with the help of technology you would do your own navigation, because you know precisely where you are, you know where the other aircraft are, and there are certain rules to do that. But this is only possible if more of European airspace is given to us.
It's this complex environment which Eurocontrol aims to simplify through painstaking political negotiation. And the task is not easy. Meanwhile, the transfer of technologies from military aviation has now brought us to the brink of a new world. A world in which complexity is reduced to ordered efficiency by satellites, computers, and automation. For better or worse, it's also a world which sees humanity playing a smaller and smaller role.
Madrid, speedboat 466 Mike, requesting descent.
Speedbird 466 Mike. Watch out. Initially proceed to Charlie November Romeo to Cormenal, expect runway 18. And you are clear to fly level 290.
Ladies and gentlemen, the captain. Well, as you've probably spotted, we've commenced our descent for our landing at Madrid, made up a minute or two, so we expect to be landing more or less on schedule, which is 7:45 local time. And the weather? Cloudy. Well, you can ascertain that with a mere glance out of the window. Southerly wind, so we'll be landing on the south-facing runway, 17 degrees centigrade. Well, at least they're not talking about rain. Well, very shortly, because we're below 10,000 feet above the terrain, we have to stop filming because we are now going to be involved with the landing of the aircraft.
Curiously, many delays out of Britain have nothing to do with the congested European airways at all, but with the wide open spaces above the Atlantic, where the curvature of the Earth cuts an aircraft off from the vigilant sweep of radar. Controllers rely entirely on reports derived from a system of onboard accelerometers and gyroscopes, old technology that needs generous allowances for error. As a result, minimum separations have to be many times greater than the 5 miles allowed under radar.
Essentially, in the airspace that most people will fly through between North America and Europe, has a separation standard that requires that aircraft follow each other on the same route by at least 10 minutes, or they be laterally separated at the same, if they're at the same altitude, by 60 nautical miles. Now, obviously, when compared with 5 nautical miles of radar separation, that's a considerable difference, and that has to be set up as the airplanes enter the oceanic airspace. And that is why that even today we have capacity problems on the North Atlantic during the busy periods.
As aircraft approach the United States, their first contact is usually here, on Long Island. This is the en route control center at Ronkonkoma, which handles aircraft from their entry into US airspace until they're taken over by the approach controllers at their respective destination airfields, up and down the east coast of the United States.
Runway 86, 45, request higher. Descend, maintain 8,000. 10 altimeter 2906. 280, thank you. PT.
Our range of responsibility is in the North Atlantic Ocean and the Caribbean Sea. As you can see on the depiction to my left here, aircraft that are leaving Western Europe, destined for the United States of America. We also see aircraft that have left Europe on their way to South America, And then we see aircraft that are transitioning between the Caribbean Sea and destinations in America and Canada as well. This aggregate view represents aircraft in a non-radar environment. There is no direct communications between these aircraft and this facility. It's done through a teletype system with a third party intervening between us and the airplanes. It's a rather antiquated way of doing business. It's rather inefficient. Results in a great deal of separation between airplanes, in some instances up to 80 miles between airplanes, versus on the domestic or the radar environment where we have 3 and 5 miles of separation between airplanes.
Soon all that will change. In Operation Desert Storm, satellites orbiting the Earth enabled Allied troops and tanks to find their location in featureless desert. But equally important, they gave Allied aircraft a precise indication of where they were in relation to each other. The same can now be done for civil aircraft. In June this year, the last in a constellation of 24 global positioning satellites was launched into orbit 12,000 miles above the Earth. An aircraft flying anywhere above the globe has line of sight with a minimum of 4 at any time. This enables it to locate itself in 3 dimensions within 100 meters. This technique was used by the military on both sides during the Cold War. But it's now on offer to the world's commercial airlines at no cost, for the moment at least. With a communication satellite in place, controllers can locate an aircraft with even greater accuracy than they could with ground-based radar. Such precision allows aircraft to fly much closer together over the world's oceans without any compromise on safety. With the right box of tricks on board, the aircraft has all that's needed for automatic dependent surveillance, ADS.
ADS is a black box in the airplane that will automatically squirt out the position of the airplane via digital data link at predetermined time intervals. And they can be predetermined and can be varied. Like if it's a low traffic area, the position report might be squirted out every 20 minutes or maybe even longer. If it's in a high traffic area, it might be as 5 minutes. It could be even less. It can be down into the seconds. And it can be determined as necessary. If we get into a busy traffic scenario right now, we can input the information into the computer and it will request the automatic reports from the airplanes, and the pilot doesn't do anything. It's just done automatically by digital data link.
ADS is now on trial and could be reducing Atlantic separations within the next 5 years. But there are other technologies in the pipeline. In the US, an onboard collision avoidance system called TCAS is already compulsory. TCAS wasn't invented here, but European airlines who venture into US airspace are having to take it seriously.
We're in the Boeing 767 simulator at the moment in order to contrive in broad daylight a collision and to have a look at the instrument which has been fitted, which is going to prevent that. It is in fact called TCAS, Traffic Collision Avoidance System, and here it is in the form of a modified vertical speed indicator. And already you can see a blue diamond with the symbol +7. So that means that there's an aircraft 700 feet above us descending towards us. In fact, if we look out of the window, we can see it actually coming towards us at this moment. As it gets closer, we can reduce the scale. It's on 16 nautical miles, and I'm reducing it now to 8. And in a moment, that same aircraft will appear, there it is, at 12 o'clock on the little screen. It's now only 500 feet above us, descending, and because of its proximity, the blue diamond has now filled in so that it's all blue.
Traffic, traffic. Descend, descend, descend.
Now a solid yellow circle, 300 feet above us, 200 feet above us, and I'm now going to change the scale down to just 4 nautical miles. And I'm getting a resolution advisory to descend, which I'm going to do now, but not quite as much as I ought to, so that you can see the aircraft flying directly over us.
Increase descent. Increase descent.
And we've avoided what would have been a collision.
without TCAS, the chances of collision at cruising altitude are minuscule. There's a rather perverse grain of truth in the idea that because of the huge amount of space outside the airways, there'd be even less risk if planes were allowed to fly randomly without passing through corridors in the sky. Airliners are much more vulnerable when they're landing. 200 or 300 tons of metal and flesh approaching a concrete strip at 180 miles an hour. Suddenly, the number of escape routes from disaster is dramatically narrowed. In calm and clear weather, landing is not a problem. But at other times, the results of an error can be catastrophic.
The crash happened as the pilot made a third attempt at a landing in stormy weather. There was heavy fog and poor visibility. The aircraft crashed into a hillside about 30 miles from the airport.
In many parts of the world, flights can still be diverted hundreds of miles because landing conditions at one airport are too dangerous. Never mind the inconvenience to passengers, getting them down alive is paramount. But soon it should be possible to land in atrocious visibility anywhere in the world, without any help from outside the cockpit. The oldest technique of all is called ILS, the Instrument Landing System. Originating from the Second World War, it's based on an approach path generated by two radio beams, one for horizontal and one for vertical positioning. The pilot uses instruments in the cockpit to line the aircraft up and bring it down a slope of 3 degrees, with scarcely a glance through the window.
Well, we have here a simulation of an airplane flying through airspace. In this particular case, it's the San Francisco airspace. We're coming into the San Francisco International Airport directly ahead. You can't see it very well because it's covered by fog, as it often is in San Francisco. If you look around, you can see quite well for most of the surrounding scenery. You can see the bridge in the lower right-hand corner. And straight ahead, beyond that land straight ahead, is the Pacific Ocean. Here we have good visual conditions, and we could fly straight in visually as we could in a car. Below and ahead of us is a fog bank, which is obscuring our view of the runway. So what we have is we have special instruments to allow us to fly when we can't see out the window. The upper one, which we call the artificial horizon, allows us to make sure that we continue flying right side up when we can't see the horizon outside. You can see a line across there which simulates the horizon. Below we have what's called the horizontal situation indicator, and this shows us a number of different information on the same instrument. One of it shows us the heading around the outside, but maybe more importantly for this purpose is that we have needles in the center and on the side which show us our path down the instrument landing system approach. If we look at the center needle, which is just very slightly off to the right, this shows us whether we're to the right or left of the desired path that will take us down to the runway. The needle over on the left side shows us whether we're above or below. Now, you would not be allowed to film this in an actual aircraft, of course, because at this kind of procedure it's very intricate and they wouldn't want interference in the cockpit. However, since this is only a simulation, that's not a problem. So we're probably just about to hit the fog bank, and as you'll see in just a moment, the screen will completely white out. Now, we can't see anything out of the front window of the airplane. However, the instruments that I have allow me both to fly the airplane and to continue to follow the straight line which will take us down to the runway. We're coming down to 300 feet altitude right now, and we're going to have to break out of the bank. And as you can see, we're just starting to break out of the bank. You can just see the runway lights, the orange in the foreground. And now we're coming down through 120 feet. And so now we're fine. We're in a perfect position for a landing.
But ILS has its limitations. The beams are straight and don't allow the aircraft to make a curved approach in mountainous terrain. Interference from local radio frequencies can also upset the signal. A more advanced system can counter both problems. Based on microwaves, it allows an aircraft to locate itself in 3 dimensions, enabling the pilot to make a curved approach. At the same time, microwaves are impervious from local radio interference. But MLS, as it's called, would be extremely expensive to install on all the world's major runways. And in the meantime, some are arguing that the increasing accuracy of global positioning could render MLS redundant. But there's another onboard technology that needs neither satellites nor radio beams from the runway. Military fighters have long had the ability to fly at very low level using a device called a HUD, or head-up display. The display is based on information about the surrounding landscape generated from computers. It's then reflected on a glass screen in front of the pilot's eyes. Commercial airlines are now experimenting with a sensor which produces an outline perspective of the runway itself. This responds precisely to the behavior of the pilot, enabling him to land without any help at all from the ground. ADS, MLS, TCAS. There are several alphabets of new technologies transforming the way pilots are guided through the skies. Gradually, the human involvement in the mechanics of flight is being eroded away. With so many computer-based technologies, how long will it be before we will allow ourselves to be flown in a pilotless plane? Military experience tells us that projectiles can follow complex routings without the need for onboard guidance from humans. Desert Storm showed how cruise missiles could easily find their way from the Persian Gulf to a particular street in Baghdad. With such precision on offer, and with so many accidents caused by human error, would passengers feel happier without a pilot in the cockpit?
I wouldn't want to be on the first flight, but I guess I would... It wouldn't worry me if the same thing, if a track record were developed that was a safe way to fly aircraft and it was demonstrated that was okay, I wouldn't have a problem with that.
I feel that, for me, that the pilot ought to be there. We ought to have the human factor there as well, because no machine is infallible. It's programmed by man and it can make mistakes.
I don't have a lot of faith in computers. I've seen computers crash. I just want to make sure they don't crash my airplane.
Helicopter 671 is leaving the TC-8 to the northwest. Radar service is terminated. Squawk 1200, frequency change approved. Good day.
But perhaps the decisive factor is that humanity has yet to devise a computer that doesn't want to die, that needs to procreate and generate yet more computers.
5,000, expect 6,000.
Human beings also have certain talents, which today's computers can't hope to match.
There may come a time when we are forced into having an air traffic control system that didn't have controllers. What's the role of the computer and what's the role of the human in doing air traffic control? One of the things we've learned about artificial intelligence is that it's pretty good in doing what we've now learned physiologically as being left side activities, sequential, orderly, logical processing. What it's bad at doing is creative things. What it's bad at doing is responding to unplanned emergencies. What it's bad at doing is doing pattern recognition. And it turns out that controllers are brilliant at pattern recognition.
And there's another argument for keeping humans in the loop. Automated systems are achingly vulnerable to sabotage. The Civil Aviation Authority is on record declaring that a child with the right kind of transmitter could knock out the global positioning satellite as a precision aid for all the airports of a major city. But if automation has to be limited, and airports aren't going to seize up with the escalating load of travellers, how is the system going to cope? One idea is to have a smaller number of larger planes. The biggest in service at the moment is the Boeing 747. It can carry well over 400 people and weighs over 300 tons. The first flight by the Wright brothers was shorter than the length of a 747. But how much bigger can we go?
Technically, there's no reason why one shouldn't be able to build an aircraft for 800 passengers or 1,000 passengers. The real difficulty is finding enough routes on which such large aircraft could operate. And obviously, the larger the aircraft becomes, the smaller is the number of routes on which you can fly those aircraft, and therefore the smaller is the number of aircraft you can build. But manufacturers need to have a large production run in order to make the production of those aircraft economically viable. And that's the key, you see. And that is why we see that the big manufacturers like Boeing and Airbus are actually talking about cooperating on building a very large size aircraft, because if they do it separately, the chances are they won't be able to produce enough.
And there are other thoughts as well. In an emergency, how easy would it be to evacuate a jet full of 800 people? And should the unthinkable happen, could an airline recover from a crash that kills 1,000 of its customers at one go? Then there are the airports. Even handling existing jumbos, immigration and customs can be painfully tedious. How could the flow of passengers be handled with aircraft twice the size of today's biggest, especially if 3 or 4 arrive at the same time?
The existing airports just couldn't cope with them. For example, the gate lounges where people sit before they board the aircraft now might have a capacity of 400 or 500. They couldn't cope with the larger aircraft. The fingers that are attached to the side of the aircraft for people to walk on and off, there are not enough of them. We'd need more exits from the aircraft to get people off in time, so we'd have to build new fingers or modify the existing ones. The turning space that the aircraft needs on the ground with a larger wingspan would have to be greater. The turning space because of the length of the aircraft. Virtually everything at the airport that handles aircraft or deals with the aircraft would need to be changed. And since the number of aircraft is likely to be small, because the number of routes on which you could use them is going to be small, that means a lot of expenditure by the airport to handle a relatively small number of aircraft that will be of this very large size. And from the airport's point of view, it's not economic at all to do that.
Another solution would be to build new airports, but their environmental impact is enormous. In any developed country, a new aerodrome will hit stiff local opposition. Building them out to sea is one way of getting round this. That's what the Japanese have done with their new Kansai airport, due to be opened next year. But it's expensive, and no option at all for landlocked countries. The third option would be to make existing airports very much bigger, and that's precisely what's happening in the United States. This is a computer mock-up of 3 projected parallel runways for Denver Airport. The thought of 3 runways at Heathrow is already filling the locals with horror, but for Denver, this is just a start.
Initially, they will open with 5 runways, 3 north-south and 2 east-west for probably departures. The long-range plan for Denver is to have 12 runways, which will carry us well into the next century. Right now, they're going to open with 5, hopefully add another runway within 1 year to bring it up to 6. I believe the 7th runway is scheduled whenever they reach 1.5 million or 1.6 million operations, and then gradually move up to the full total 12 runway complement will be when the traffic demand is there. 12 runways may be very futuristic, and it may be quite a few years before we see all 12. We don't actually know which way aviation is going to go. If we go to larger aircraft, we may need fewer. However, the way aviation has grown in the past, we'll go to larger, then we'll have a lot of large aircraft.
The hazards of predicting such a huge increase in demand are legendary. In 1973, the Arab oil embargo led to a quadrupling in the price of fuel, with a profound effect on the economy of the world. The demand for mass air transport plummeted. Thousands in the aviation industry were laid off, and there was a 10-year moratorium on recruitment. In the 1990s, what princely cot or rural crib is nurturing the dreams of a 21st century tyrant? A man with the capacity to hold the world's fuel reserves to ransom. It can take a generation and billions of pounds to develop a new airport or fleet of jets. With so much at stake, how can you know that you're taking the right decision?
You can't predict these unforeseen events, but what you do is you ignore them, precisely because, for two reasons. You can't predict them, and secondly, whatever happens, the impact of those events is relatively short term. In other words, it'll be between 1 and 3 or 4 or 5 years. After that, you know, and the past experience shows that, after those 3 or 4 or 5 years, we get back on the same level of growth as we had before. So the assumption you make is that the long-term growth rate is going to be between 4 and 6%. But within that period of time, you will get years when things will go disastrously badly and years when the industry will do very well, demand will be very high. And that's what you're planning for. You ignore the short-term fluctuations due to unforeseen events.
In an unpredictable world, one near certainty is staring us in the face. That the economic lead in the 21st century will be taken not in Europe or the United States, but a region that used to rub its fiscal shoulders with the rest of the Third World. In aviation at least, the serious money is going to be made here on the Pacific Rim. Singapore, Osaka, Kuala Lumpur, Beijing, Shanghai, Hong Kong. The names are whetting the appetites of big business already. The traffic control systems being installed here are unencumbered by the political baggage which has so bedeviled Europe with its piecemeal evolution.
Man is infinitely inventive and also wants to travel. And what will happen is that growth will slow down in certain parts of the world as people